Thank you, Chen. I'm Yukun Chen from Suzhou University of Science and Technology. Today, my talk is about a novel two-stage game model for the pricing management of edge computing resource in blockchain system. This is a joint work with my project postgraduate my students Chen Jingmian and Xu Zhiqi. Yeah. My talk includes five parts. The first part is the introduction. Sorry. Yeah. What's wrong? Yeah. Yeah. The blockchain is a public distributed ledger which records a set of transactions. Yeah. Transactions are verified through a decentralized consensus process among the trustless agents before attaching to the chain. The blockchain owns different kinds of advantages. For example, it is the decentralized network. It's a tamper-proof ledger, transparent transaction, and trustless but secure trading. The key technique in blockchain system is the consensus protocol. The consensus protocol guarantees achieving the agreement among the nodes. It has a good consensus protocol must satisfy following properties. The first one is the correctness, and then the consistency and the traceability. There are different kinds of consensus protocols applied in different blockchain systems, among which the most popular one is POW protocol, that is the proof of work protocol. So POW protocol is the consensus mechanisms for achieving agreement. What's wrong? Can you hear me?
Yes.
Yeah. A core idea of POW ensures the consistency of data and the security of consensus through the computing power competition of distributed nodes. The POW achieved the consensus by solving a mathematical puzzle, that is by finding a hash value. The hash puzzle problem is difficult to solve, but easy to verify. Yeah. We are very interested about the incentive compatibility of POW. The first node that solves the puzzle can broadcast the verified block to the blockchain network and obtain the reward and the transaction fee. The process of solving puzzle and obtaining the reward is called mining, and the participants who solve the puzzle are called the miners. Yeah. In 2008, Nakamoto published the white paper which declared the beginning of Bitcoin. Starting from the Bitcoin, many cryptocurrencies have been proposed to achieve different goals. So in the website of the coinmarket.com, we can see there are about nearly 8,000 cryptocurrencies in the world, and the market is about 33,000 in the world. So there are a lot of the number is very high, it's very large. The price from the picture we can see the price of the Bitcoin fluctuated frequently. In the price of Bitcoin fluctuate a lot in the past several years. Recently, we can see its price continues to rise and obtains its price about $18,000 one BTC. Since mining needs the tremendous computational power, it is difficult for miners with small, even medium size to find a new block. This results in a large variance in rewards across miners, even with a long time horizon of a few months. The majority of miners would get no reward. So miners who desire a steady income often cooperate and join together to form a mining pool, which is managed by a pool manager. So when a pool member solves the hash puzzle, the block is mined and the rewards are distributed among the pool members. As we know that the price of the Bitcoin is always continues to rise. It's near about 18,000 per one in Bitcoin. So the mining manager, the pool manager may be optimistic about the price of the Bitcoin in the future. So it will have two choices: hire more miners to mine the block, or buy edge computing resources. Because the pool must compete to make profit through the block mining, which shall cost them high computational power. So each pool have note that each pool has an initial computational power, and some of them may purchase a certain amount of computing resource to speed up the mining process from an edge computing resource provider. So just we ask, there are two choices for a pool manager, that he shall make decision to hire more miners or buy edge computing resource from the other private providers. From the other side, for the edge computing provider, he also should make a decision, that is how to price and allocate its computing resources, computing service to different pools. It's the introduction. And for this problem, we give a model and some preliminaries. We construct a novel two-stage game for the pricing management of the edge computing resource in blockchain system. In the stage one, the provider set the service price, that is the computing resource price. In the second two, we construct an evolutionary game for pools to pursue the evolutionary stable solutions. In our setting, we studied a public blockchain system, which is the POW-based protocol. There is one edge computing resource provider, and there are two pools, pool 1 and pool 2 in the system. Each pool has its initial computational power of pool I. So we denote the initial computational power denoted by the WI. QI is the demands from edge computing resource provider. So for pool, we shall compute the relative computing power gamma I. From the gamma I, we can see it's the ratio. It is the ratio. This is the computational power of total power of the pool I and the total power in the system. Which the relative computing power gamma is just a ratio. This figure shows the relationship between the provider, and the pools. The process of successfully mining a block includes two steps: the mining step and the propagation step. In the mining step, the probability that pool I competes to be the first one to solve POW puzzle is directly proportional to its relative computing power gamma I. In the propagation step, the mined block is likely to be discarded because of long latency. The long latency depends on the size of the mined block. It means that a larger size block leads to a larger latency, and a higher chance suffers often. Yeah. When the propagation time tau I is denoted by tau I of poor I is linear to the block size Si. So we the tau I the propagation time tau I is equal to Z times Si. Lambda, the parameter lambda is the arrival rate of a new block following the Poisson distribution. The probability of a block being orphaned is this. The probability orphaned is 1 minus e to the power of minor lambda times z times si. So the probability of successfully mining a block by poor I and such a block reaches the consensus is the probability is gamma I times the non-orphaned probability. So it is the gamma I times e to the power of minor lambda times z times si. And so we just computed the probability of the successfully mining a block. And then it is easy for us to compute the individual expected utility of poor I. It's just the formula. The first part is the expected income, and the last part is the cost to buy the resource from the edge computing provider. The big R represents the mining reward, that is the 6.225 BTC per a block for a block. The small r is the unit transaction fee for each transaction, and R times SI is the total transaction fee. P times QI is just the cost of purchasing the edge computing resource. For the pricing management, we construct a two-stage game formulation. Just as we said, in two stage. In the stage one, the provider as the leader sets the service price, and in the second stage, stage two pools as followers decide their evolutionary stable computing resource demands through continuous learning and adjustment in the second stage. So we formulate an evolutionary game between two pools in stage two and propose an optimization problem for the leader in the stage one. Yeah, and to construct the two stage to construct in order to construct the evolutionary game in stage two, we should discuss the payoff of the different under the different strategy profile. So each in our evolutionary game, each pool has two strategies. One is buy and the other is not buy. The strategy to buy means that the demand QI is strictly larger than zero, and the choice to a choice not buy anything, it means that the demand is equal to zero. So for two pools and two different strategy profile, we can get the payoff the matrix of two pools in the evolutionary model. So for this model, the game model, we should compute the payoff under the different strategy profile. For example, for the strategy profile buy and buy, it means that both of the two pools decide to buy the resource from the provider. So we compute the payoff. The payoff is equal to the maximal utility, And for the strategy profile buy and not buy, it means the pool two decides not buy anything, and the pool one decides to buy the resource from the provider. So the payoff for the pool one, and its payoff is the maximal utility, and the pool two, this is the pool two's payoff. By using this method, we can compute the different payoffs under different strategy profile. Yeah. For the stage one, we construct a more optimal problem subgame. We give the provider subgame, which is just to maximize its profit function. So the first part is the price times the demand, and the last part is the cost, the electric cost for to provide the service, computing service. So this formulation, the formula is represented the profit function of the provider in the stage one. Yeah. The next part we shall give the equilibrium analysis. Yeah. We use the backward conduct method to analyze the equilibrium. For the stage two, we studied the evolutionary game for the two poles. We set the parameter A and B as this, and it is easy to see such two parameters only depends on the size. So the parameter A is only depends on the S1 and B depends on the S2. For the strategy profile buy and buy, the optimal demands of pool 1 and pool 2, we can compute the optimal demands of pool 1 and pool 2 as this, like this, and also can compute the payoffs like this, and give the payoffs, the concrete payoff of the pool 1 and pool 2. By the same method, we also can compute the demand of the pool 1 and pool 2 and their payoffs under the strategy profile buy and not buy. So for the strategy profile buy and not buy, it means that pool 1 decide to buy computing resource with demand. We can compute the optimal demand like this, and the pool 2 does not buy anything. And under this profile, we also can compute the payoff like this for this strategy profile. Then continually we compute different the payoffs under the different strategy profile. So you can provide the payoff matrix of two pools in the evolutionary games. Yeah. To analyze the equilibrium for the evolutionary game, we use the standard method. First, we should set the parameters. Each pool has two strategies, buy and not buy. We use xt to denote the probability of pool 1 to buy computing resource at time t, and the yt is the probability of pool 2 to buy computing resource at time t. Then for pool 1, we can give the formula of the expected payoff when pool 1 choose to buy the resource, and the expected payoff when it does not buy the resource. And then we can compute the average expected payoff of pool 1. It's like this. And similarly, we also can compute the expected payoff when pool 2 choose to buy, and the expected payoff when pool 2 does not buy anything, and the average expected payoff of pool 2 is like this, E2. Also, by using the standard analysis method to explore the evolutionary stable strategies of an evolutionary game model, we can compute the replicator dynamic systems. So these two formulas consist of the replicator dynamic system. Now, yeah. By the stability theorem of the differential equations, all the solutions satisfying fxy equal to 0 and gxy equal to 0 are the fixed points of replicator dynamic systems. So we can get following 5 fixed points of the dynamic systems: 0, 0, 0, 1, 1, 0, 1, 1, and the x star and y star. But the x star and y star, if the x star and y star is the fixed point, they must be fall into the interval 0 to 1. Yeah, the x, y is represent the probability to choose a strategy of buy resource into the interval 0 to 1. Yeah. 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 So, yeah. And then from the replicator dynamics system, we can construct the Jacobian matrix, like the Jacobian matrix J, and given point xy, if the determinant of J is strictly larger than 0 and the trace of J strictly less than 0, then this point is an evolutionary stable solution. It is an ESS. To simplify the discussion, we denote the HKMN, and we can see under the different kind of the fixed point, we can compute the determinant of J and the trace of J in this table. From this table, we can conclude the conditions for a fixed point to be an evolutionary stable strategy. Give the conditions are like this, we can see the fixed point 0 and 0 cannot be an ESS because H is larger than 0, K larger than 0, and then the trace of J is larger than 0. It's concentrated this condition. And the fixed point 0, 1 is an ESS if and only if M is strictly less than 0. And 1, 0 is an SS if and only if N is smaller than 0. And 1, 1 is an ES if and only if M is larger than 0 and N is larger than 0. From the conditions, we can, based on the conclusions, we can continue to explore the detailed conditions under which the fixed point 0, 1, 1 is an ESS. These conditions are listed in this table. And also, furthermore, we can obtain the detailed conditions under which the fixed point 0, 1 or 1, 0 are the ESS. The conditions are listed in this table. Yeah. If we got the ESS evolutionary stable solutions, we can continue to back to the stage 1 to compute the optimal price for a provider, And yeah. For example, if 1, 1 is an ESS on the previous condition, then the demands of 2 pools are like this, and we can construct the profit function of the provider like this, and it's easy for us to compute the optimal price like this. Also, easy for us to see if the P star satisfies the conditions for ESS 1, 1, we can get the equilibrium for the 2-stage game. By the same method, we also can give the different conditions for different ESS equilibriums. Also, yeah, last we conduct some experiments. We first conduct experiment to evaluate the impacts brought by the unit transaction fee small r, in which the default parameters are set as these. Yeah. The figures demonstrate the dynamic evolutionary process of pool 1 and pool 2 respectively. It's pool 1 and it's for pool 2 from different initial probabilities choose by strategy, 0.2, 0.5, and 0.8. From the pictures, we can see the numerical results show when one is ESS, which is in accordance with our theoretical findings under the condition of A is equal to B. The speed of pool 2 is converged ESS is faster than the one of pool 1, because since the initial computing power of pool 2 is smaller than the one of pool 1, so it has greater willingness to buy the computing service. The speeds of convergence of both two pools increase with the unit transaction fee, since the increased variable reward motivates the pool to buy the computing services. And the speeds of convergence of both two pools increase with the initial probability. And then we also conduct the experiment to evaluate the impacts brought by the reward big R, which is fluctuated by the price of BTC. And can see this the picture is the result of the experiments. We also conduct a series of experiments in which the size of S2 is fixed, leading to the fixedness the parameter of B. And we want to see how the optimal price P star varies with the parameter A, and want to see whether the optimal price can be achieved or not, and to find the corresponding range of P star at which the equilibrium for the two-stage game is obtained. We got this picture is the result of the experiments. We can see this area represents the feasible area for the ESS, and the red dashed line represents the optimal price star. We can see if the price set us in this range, we can obtain the equilibrium of the two-stage game. And the same result this experiment is similar for the different conditions. So conclusion, for this problem, we construct a novel two-stage game scheme for the pricing management of edge computing resource.
If she comes back, we can let her, during the Q&A, we can let her finish. Okay. Yep. All right. Thanks everybody for attending the first session. In 2 minutes, we will have a Q&A with all the authors. And again, thanks to all the speakers for the interesting results. See you in 2 minutes.